So let's start our next section, 3.7, which is related rates. So I'm going to start by reminding us that we used the chain rule in the last section when doing implicit differentiation to find dy dx. So in this section, we're also going to use the chain rule. So now we use the chain rule to find rates of change of two or more variables, related variables, that are changing with respect to time. So let's look at this problem right now. Let's say I have a conical tank. Just means I have a cone-shaped tank here containing some water, and we're gonna drain water out of this tank. And so because this is a cone, we have a volume formula for a cone. The volume is pi over 3 r squared h. Now, remember that this is filled with water. It's got water in it. And we're draining the water, so as time goes on, the radius of the water and the height of the water depend on how much time has passed. So R and H depend on time. But what that means is because these variables here are related with this equation, it means that the volume, V, is a function of time. Secretly, the equation contains the variable t, we just can't see it. And so what we could do is we could take the derivative of both sides with respect to time, just like we did when we did implicit differentiation. Take the derivative of both sides here, and on the left you'll get dv dt, the derivative of volume with respect to time, and then over here we have pi over 3, which I'm going to factor out here, and then I have a product, so I'm going to have to use the product rule. This would be r squared times dh dt plus h, and then the derivative of r squared is 2r dr dt. So dv dt equals pi over 3 r squared dh dt 2 rh dr dt. And so we use the chain rule to compute this derivative right here. And what have we done? We've found a relationship between the rate of change of volume with respect to my other two variables, the radius and the height.